Alright, welcome to Maths Mastery. I'm Matt Stabenow. Today we are going over Unit 2, Regions Chemistry. It's where it starts to get fun. We're going into models of the atom. This really begins with Dalton, his model. It says that all elements are comprised of their own special, unique spheres. It's hard, like you can't break them up or anything. And each element has its own specific sphere, and they're all the same. Really not the best, but it's the beginning. Next, we move on to the plum pudding model. That is by J.J. Thomson after his cathode ray tube experiment. He shot a beam of negatively charged electrons down the cathode ray and saw they were attracted to a positive terminal and repelled by the negative. So we found out they were negative, and we really discovered that the atom has these little negatively charged electrons just hanging out in them. We call it the plum pudding model. It's like an old-timey food. It's like fruit cake. No one really eats it anymore, but I like to think of it better as like a chocolate chip cookie, something better known. So you think of your atom is just your cookie, it's positively charged, the red part is positively charged, and you just have these free-floating negative electrons, like chocolate chips. Next is Rutherford. Rutherford discovers that there is a densely charged positive nucleus in the center of all atoms, and they just have the electrons just floating around it, really. This was discovered through his gold foil experiment. We'll talk about that more in depth. This is a very important topic, but really small, densely positive nucleus in the center, electrons just floating around. It's small. The nucleus is small. The electrons going around it occupy most of like the space. So maybe my drawing doesn't represent that the best, but next we move on to Bohr's model. His model is very important when it comes to excitation and bright line spectra, which of course we'll talk about later in the video, but just you gotta know that he keeps the positive nucleus, and now instead of your electrons just hanging around, just floating, now they're in set energy levels orbiting the nucleus. So the closer you are to your nucleus, the lower the energy level, and so these are lower energy than these. So it's like, we'll talk about more when we talk about excitation. Just gotta know, Bohr's model had some flaws still though, so it doesn't really explain anything except hydrogen. But now, move on to quantum model. This one is the most recent, probably the most accurate model. De Broglie and Schrödinger, after they found that electrons, really any particle at like the subatomic scale, behaves both like a particle and a wave. It's more quantum mechanics. Can't really talk too in depth, but a property of these really small particles is that you can't know where it is and where it's gonna be. That's Heisenberg's uncertainty principle. You can't know the location and momentum. So basically, this model, you can't really know where the electrons are, really. So what we can do with Schrödinger's equation, very complex, we can kind of find the probability of where your electrons are around your atom. It kind of just, you have these areas around the atom called orbitals, which are like represented as like electron clouds. They're areas where it's very probable that there's an electron, and you have a bunch of orbitals going around your nucleus. That's the most modern model. You should know all of them now. Of course, the cathode ray tube experiment for the plum pudding model. I haven't drawn it yet, and I haven't explained it yet, but the gold foil experiment and Rutherford's model, and excitation with Bohr's model, which we will also cover soon. So really that's all you gotta know. These are your 5 models of the atom. Alright, we'll now talk about the gold foil experiment by Ernest Rutherford. Begins with our alpha particle. It's a helium-4 nucleus. It's more advanced now. You just have to know it's +2 charge. Kind of just sent them into a sample of gold foil. You know, gold atoms. So these are your gold atoms, and he sent his alpha particles in, and you had the experiment, you could see where the alpha particles ended up after they passed through. He discovered that most of the particles just went straight through. You can see by here. So alpha particles just went straight through uninterrupted, but some of them were deflected at sharp or grazing angles because the positive alpha particle encountered a similarly charged dense positive nucleus. Alright, so he sent his alpha particles and they hit the nucleus and they went flying off. They bounced off like this, or grazed off. So basically the discovery, like the results of this experiment, we found out that atom is mostly empty space because most of the alpha particles just went straight through it. But we found that there's a very small, densely positively charged nucleus. And when the alpha particles hit that, they bounced off at sharp angles or they just were deflected. So those are your 2 results. So previously, it just showed you the Rutherford model because of this experiment. Now you know why. Big points, empty space, dense, positive nucleus. Alright? Good. Alright, welcome back. We'll now be going over subatomic particles, stuff that make up our atom. There's notes right here, but let's bring it over here to our 3 subatomic particles that you need to know. Your protons, your neutrons, and your electrons. The 3 key things you need to know about each is their mass, their charge, and their location. The mass is, of course, the mass of the particle, and it will deem how the number of that particle affects the mass of the atom. It's kind of simple. Let's just go over. Protons, mass of 1 AMU, that's your unit, atomic mass unit. Neutrons are also 1. Your electrons, their masses are so small, you pretty much just ignore it. So say 0. And next is your charge, your electric charge, either positive or negative. And we go by units, so it'll just be either +1 or -1. So our protons are +1, so P for positive. Your electrons are -1 for the same factor. And then your neutrons, neutron, neutral. Hopefully that'll help you remember that it's charge of 0. Now finally, the location of these particles. Alright, we already explained models, and you should have known that your electrons are outside because of like the gold foil experiment and Bohr model, you should know this stuff. Electron location, I gotta write this out, but it's just outside the nucleus. Wait, that looks terrible, but you should just know electrons are outside your nucleus. Next, our protons and our neutrons, they're together in our nucleus. So you should know from the gold foil experiment that the nucleus is a dense positive charge. So if the nucleus is positive, then it has to have your positive protons, of course. Your neutrons also hang out with your protons inside the nucleus. Just know that. I'll write it big for both. Nucleus. Both. Alright, these are your 3 subatomic particles, you should know their masses, their charges, and their locations. And we'll get to it, but your number of protons and your number of neutrons impacts the mass of your atom, and the number of protons compared to the number of electrons gives you the overall charge of like an ion. Or if they're equal, it's a neutral atom. Alright, now that we talked about our subatomic particles, we're going to do a little exercise based off what we just learned. So I put up in a little example right here, helium-4. If you're paying attention in the previous segment of the video, you know an alpha particle is the nucleus of this atom, but that's just kind of like a fun fact. So you could like pause the video right now and do this. If you just want to keep watching, I'll just do it and then I'll explain this. Hopefully you know this because you know there's a review video. This should all know this stuff already, but okay, we're just gonna go right in there. Alright, so our number of protons for our helium-4 atom, I drew it right here so you can just count. It's 2. Next is the number of neutrons, 2. And our number of electrons, since this is an atom, it's electrically neutral. So our electrons need to equal our protons because the -2 of the electrons has to balance out with the +2 of the protons. So, okay. Alright, now I was kind of going through this a little bit, but I'm gonna hop right in. Our mass number of our atom, if you remember, electrons, negligible mass, and then our neutrons and our protons both had masses of 1 AMU each. So you can find your mass number by just adding your number of protons and your number of neutrons together. Because, well, 2 protons each with the mass of 1, and then 2 neutrons each with the mass of 1, it's 4. 4. AMU. I don't know if you need units, but it's just helpful. Atomic number. So this is how your elements are sorted on your periodic table, and each element has its own unique atomic number. Your atomic number is the number of protons in your nucleus. So you already counted a number of protons, so it's just 2. Helium is number 2 on the periodic table. You could know that as well. And then finally, our nuclear charge. This is a concept that will become important for the unit. I think this unit, maybe just in the future you'll need to know, but the nuclear charge, kind of like just know what it is just based off what it is. It's the charge of your nucleus. So as we already know, our neutrons are neutral, no effect on charge, but our protons have a charge of +1. So if you add up our 2 protons, you get +2. So atomic number and nuclear charge are both found using the number of protons, and then your mass number is just the sum of your neutrons and your protons. So it's really good exercise to like find what values you can get using your number of subatomic particles. Alright, once again going off our idea of our subatomic particles, we now move on to ions. Ions are just atoms that they have a change in their overall charge due to a gain or a loss in electrons. So let's just walk through a quick little example here of hydrogen, number 1 on the periodic table, which tells you there's 1 proton in its nucleus. Also, we're just doing helium-1, the isotope, so no neutrons. There's versions of hydrogen with neutrons, deuterium and tritium, if you need to know, but that is total junk. You do not need to know that. Or maybe you do, I don't know. Go over it in nuclear. But that was a little tangent. Let's go straight to hydrogen. We got our good old hydrogen atom. Overall charge is 0, because your +1 of your nucleus from your 1 proton is balanced out by the -1 of your 1 electron. Next, we go over to hydride. The hydrogen changed to hydride. You add "ide" to the end of a negative ion. It's called an anion. And a negative ion is called an anion. A positive ion is called a cation, because the cat ions are positive. It's a quick little thing to remember it by. So just need to know your hydrogen gained an extra electron, -2 from your electrons, +1 from your nucleus, 1 proton, -1 overall. And it got bigger. That's a trend you need to know. Talk about that more in periodic trends, I believe. Or maybe this, I don't know. I don't really know. And finally, we got hydrogen cation. So this right here has an overall charge of +1 because it lost its electron. This guy left, and now it's just floating around +1. Those are will float around in your acid solutions. Arrhenius acid. That's acid and bases. You don't need to know that yet. Well, you should know it because it's a review video, but yeah, this is a quick little example of ions. Your negative anion and your positive cation. And you should know that your anions, their names change. It goes hydrogen to hydride. If it was chlorine, it'd go to chloride, iodide, fluoride, oxide. Alright, we now move on to isotopes. Isotopes are kind of like ions. They're alterations in your atom based off differences in numbers of your subatomic particles. But isotopes deal with differences in the number of neutrons in your atom. So how an ion was an atom that had a different number of electrons and that caused a different overall charge value, isotopes are the same atom, like our example carbons, but the different number of neutrons alters the mass number of our atom. So really quick, you need to go over the difference between mass number and atomic mass. The atomic mass is a weighted average of the natural occurring isotopes of an element. There's an equation that you should know. It's peeking in the top right corner right there, but we'll go over that more. But really, our mass number, we talked about it previously. That's the mass of our individual atom of a certain isotope. So our mass number of our carbon-12 is 12 right there, or 14 in carbon-14. This difference is caused by 2 additional neutrons in our carbon-14, because we already know that the atom's identity, like which element it is determined by its number of protons. So if you were to alter the number of protons between these two, you wouldn't have carbon for both of them. So your mass has to change between isotopes due to different numbers of neutrons. Alright, we have on display here 3 different notations for separate isotopes of carbon. We have carbon-12 written out this way, and this way. They all just mean the same thing. It's different ways to write it. As you can see, it's all focused around the mass number 12. 14, C14. C with a 14 in the top left corner, or just write out carbon with 14. So really, just need to know isotopes are same element, different number of neutrons, which means a different mass number. Next, we will move on to going over an average atomic mass. I wrote out the formula. It's also on your reference table on the back, so you don't really have to memorize this. You can just check it whenever you want. But the average atomic mass, as I've already said, is not the mass of your individual atom. It's a weighted average of all the naturally occurring isotopes of an element. So on your periodic table, it gives the average atomic mass of each element. It just basically means like, so say our carbon 12, carbon 14 example. Carbon 12 is more common than carbon 14 because it's radioactively stable. Nuclear unit, gonna go over that eventually. But yeah, so our atomic mass would be closer to 12 because carbon 12 is more common. I'll just talk you through the formula. So you take the mass of your isotope and multiply it by the percent abundance, which on the question it should give it to you. So you're basically plugging in values that the question should give you into this equation. And then this dot 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 implies that there's a continuation, because if you find the mass of one isotopes, it's going to come out. Yeah. So you just take your isotope 1, so say carbon 12 times the percent abundance, let's say like 80, and then plus carbon 14, so you plug in 14 because that's the mass number, times whatever that abundance is, like 20. Just have it nice. So 12 times 80 plus 14 times 20, add that all together, and then you divide it by 100, and that should give you a percentage. Actually, no, not a percentage. Don't believe what I just said. It should give you your average atomic mass for carbon. It's very nice. It's on your chemistry periodic table. All right. Now we're going over the concept of PELs. That stands for principal energy levels. It's just how your electrons sort into different energy levels symbolized by rings in the Bohr models, which we have already talked about. So, whole thing about the Bohr model was that the electrons don't just hang out around the nucleus, they sort into different energy levels based off how close they are. So if we look at a quick little example I drew of an atom, we have two distinct rings that we can see. We have N1 and N2. That is your principal energy level number, I believe, or principal quantum number. I don't think the name is too specific. So we have N1 and N2. N1 is the closest to our nucleus, so it is the lowest energy because it's just hanging out. The electrons, the whole positive negative attraction is strongest at N1, and it's also the lowest energy. I don't really know how to equate that. So the electrons are just really chill. They're just like happy to be so close to the nucleus. And then as you go further out, they get like, they wish they were closer. So that's kind of why N1 fills up first, because they love being close, and then N2 and then N3, and then there's exceptions, but that's AP Chem. Really, further out is higher energy, closer in is lower energy, happier, stabler, stronger attraction, whole lot of stuff. They sort into energy levels. Okay, so now we're going to transition into finding max number of electrons in a PEL. It's a quick little formula right here for you. You could use this formula, you can memorize it, it is not provided, where you just have your principal energy level number, so like N1, N2, N3, just plug it in, square it, and multiply it by 2. I wrote out the answers, like the results of using this equation for your different energy levels, so I have that there for you. Nice and easy. Really, finding max numbers of electrons in a PEL. You can also find this out using the periodic table on your reference table. In the bottom left corner of each element's little box, I'd say, it has it provides you with a layout of where the electrons are in the different levels. So like oxygen, it says 2-6 because 2 in N1, 6 in N2. Really, it's just know your formula, you memorize these, or you could check your reference table. Alright, next we're going over concept of valence electrons. This is one of the most crucial ideas in the whole curriculum. The idea that your outer electrons are really in charge of like all your bonding and all that stuff, chemical reactivity, like chemical properties, all that stuff depends on your valence electrons. So I didn't even define it yet, so we're going to hop right into that. Your valence electrons are the electrons that occupy the outermost ring of your atom. So right here I drew oxygen. So you see it has 8 in total, 2 at N1 and 6 at N2. So these 6 at N2 are your valence electrons. Over here, I also drew lithium, 3 in total, 1 valence electron. So the number of valence electrons really determines how you bond ionically. It can really help in determining like covalent molecules, like how to draw dot diagrams for that. We'll cover all that when we get to it in upcoming unit. I don't know the number, but cover it more. This whole idea, your valence electrons, your highest energy electrons. These are also the electrons that you lose in an ion. Previous segment of the video. So Li is a metal. He wants to form an ion. He loses his valence electron. Oxygen, on the other hand, since he has 6 in the outer ring, he wants to gain 2 to get 8 in the outer ring. This is the whole idea of a stable octet. You want 8 electrons in your valence ring. It'll really help. It's really good. And depending on if it's closer to 8 or closer to just losing all of them, going to 0, that depends if you form positive or negative ions. I feel like I've talked maybe a bit too much, but yeah, big concept, gonna cover it more later. Welcome back. We are now going to talk about emission/electron transitions. So as we previously talked about, our Bohr model stated that our electrons orbit our nucleus in certain energy levels, principal energy levels, PELs, we also talked about that. And now we're going to talk about a big concept related to that topic, emission and electron transitions. So, I don't know if I previously stated it, but our electrons like to occupy the PELs closer to the nucleus. Those are lower energy levels, negative attracted to positive, they want to be together, think about magnets. So I drew out a bunch of lithium atoms, 3 electrons. So it's just for the example. So right here we have our lithium atom in the ground state. Our ground state means that our electrons fill into the lowest possible PELs, which makes sense. 2, which is the maximum you can have in the first, and then your extra 1 is just bumped into the second PEL. So right here we have an excitation. It's any energy added into the atom. It's usually, think about light, really mostly like higher energy wavelengths, like ultraviolet maybe. So you hit your atom with this light, and I drew it right here. Our electron in the outer PEL moved to a higher energy level. It got further away. It went from 2 to 3. Of course, this could also happen with, say, our second move to our fourth, our third, our first PEL electron might have moved to the second PEL. You never really know. Kind of just shifts out. It goes from the lowest possible energy state to a higher energy state. So this is called the excited state because it got hit with the excitation, of course. The excited state has an electron where it shouldn't be. So it's like this, and then it can return back to our ground state. See, our outermost electron came from the third back to the second where it belongs, and it released an emission, which is also light. A big concept with this is that we can identify elements using their bright line spectra, which is just the different emissions an excited atom of that element can give off. But yeah, that's a big thing. You can go from your ground with an excitation to an excited state where a lower PeL electron moves to a higher energy, higher number PeL. So second to third in our example, and then it goes back down by releasing energy, which we'll talk about again when I go into bright line emission spectrums. Alright, now we're moving on to bright line spectrums. As I just said, this all revolves around the excitation of atoms, so that's a big thing. So when our atom gets excited and it goes back to the ground state and it releases its emission, that emission is a certain energy level depending on the jump that the electron made. So you can identify elements because they all have unique bright line spectrums. A bright line spectrum is just, like I drew them out here, not the best, but this is a jump, this is a jump, this is a jump, this is a jump. These are all different wavelengths of light the excited atom can emit based off what electron jumped, how far it jumped, all sorts of stuff. But every element is unique, so that's a big thing. So right here, this is one element, this is a different one. I just made these up, I just drew them. They're sort of based off wavelengths, so like you have your higher wavelengths right here. I think I worded that wrong. Just blue. Roy G. Biv. Alright, we're going to end off Unit 2 by going over orbital notation, which really isn't tested on the Regents, but is fun to know and is important if you go into AP Chem, which I believe a lot of you should. If you're putting in the work and watching these videos, and I feel like you have the work ethic to take AP Chemistry. So this is all based off our wave, our orbital model. Remember that? I filmed that like a month ago, but you watched that like 6 minutes ago. But if you remember, we found out that can't really know where an electron is, so we solved it by using orbitals. Orbitals are areas where you're likely to find electrons. It's a big thing. It's like a cloud. You can see it as a cloud, but it's like really just like an area where you could find an electron. It's given by the Schrödinger wave equation. It's really cool. So right here, I wrote out sodium using principal energy levels to demonstrate. So N1 has 2 electrons, N2 has 8 electrons, and N3 has 1 electron. But if you write it in orbital notation, you see it like this. So this, alright, first I have to explain how we break up PeLs. PeLs get broken up into sublevels, and then the sublevels get broken up into their orbitals. Orbitals are, as I already defined, areas where you're highly likely to find the electron, and they are, you find 2 electrons per orbital. So I drew out some orbitals. They're different shapes based off different letters, and then the sublevels of the different letters. So, like this is an S. It's just like a sphere around your nucleus. You're gonna find the electron. And then these are your P's. Your P has 3 orbitals, so it's 3 shapes. Got, like, it's kind of just like a balloon pinched in the middle. Like 2 balloons like joined at the middle. So this is 1, 2, 3. They all go in different axes, X, Y, and Z. So kind of try to draw it out like this. Yeah. It's cool. It's cool to know the shapes. So now we're going to explain the orbital notation. So you could maybe do this for fun if you want. So first is the number in the beginning. That indicates PeL. That's nice and familiar. That indicates that the 1 in 1s2 means it's from PeL number 1, N1. So S means the shape. The letter means the shape or the sub-level that it belongs to. So subbubble is just a shape. So the S means that it's in this shape. It's the circle little sphere around the nucleus. And then the superscript, I believe it's called, indicates how many electrons you have there. 2, because 2 in your 2s. And then as we go into our bigger PELs, we have more sublevels and more orbitals. So in the second principal energy level, we have 2 sublevels, an S and a P. The S is the same as it was before, same thing, same like orbital with its 2 electrons in the shape of a sphere, and then our 2p6. The P sublevel has 3 orbitals in it, as I drew out. Hopefully you understand my drawing, but it's got the balloons going up and down, balloons going side to side, and the balloons going towards you as you look at it. So each orbital in the sublevel has 2 electrons each. So 2 times 3 is 6 in total. So you have 6 electrons in the P sublevel and 2 in the S, which gives you a grand total of 8. Well, stable octet, 8 electrons, remember? And then our third PEL in sodium has only 1 electron, so it's just 1 electron in your little sphere orbital. So now we're going to kind of go off and look at something cool. It's totally, you don't need to know any of this really. You kind of need to know sublevels and stuff, but you don't need to know how to write that out. You don't need to know the diagram, like the electron spins. So electrons have spin. They're not really spinning. It's they exhibit properties like angular momentum. That's what it is. Angular momentum, physics. Take AP Physics 1, like me. It's a fun class. But, so, your electrons in an orbital, they have to have opposite spin. That's a big thing. And as you're filling up an orbital, as you fill up a sublevel, you fill up each individual orbital with an electron with parallel spin to the. So if I'll draw it out. So if you have an empty P sublevel, as you fill it up, it goes like this. It fills up, half fills each orbital with parallel spin electrons before it starts filling it in, completing each one. So, yeah, that's cool. Now we go into xenon. This is totally irrelevant, but you really get to see how your bigger sublevels, like say N3 has an S, a P, and then a D as well. Each one gets bigger, more orbitals, more crazy shapes, so couldn't understand that drawing. If I tried to draw out a D orbital, you'd really be confused. But yeah, and then you see it fills in different orders, the first one, the first PEL fills up, then the second PEL, and then the third PEL, and then it goes to the fourth, and then it goes back to the third, and then back to the fourth, the fifth, the fourth, the fifth. It's crazy. And then there's an F orbital. It's even crazier. It has 14. It has seven orbitals. So I really went on a tangent. If you enjoyed that, that's cool. Take AP Chemistry. We actually learned this stuff better than I explained it, but forgot to cover it in the actual video. So hopefully you survived long enough to hear about electronicism. It's when an ion and an atom have the same electron notation. So when sodium becomes the sodium ion and goes to sodium +1, it loses this electron, right? Now what atom has this same notation? Neon. So neon and sodium +1 are isoelectronic, and then say if you had oxygen -2 would also be 2,8. So that would also be isoelectronic. That's just another thing you need to know. It's this is a fun unit. I really like this stuff. If you like it too, if like my explanation left you hungry for more, you should take AP Chemistry. So, that's a wrap.